Hello, today we're going to go over one of my favorite problems to give students when we're talking about quadratics, and that is an applicable problem to building a fence. So this is Mrs. Brown, and her class will raise rabbits for their spring science fair. They have 24 feet of fencing, and they can build that a rectangular rabbit pen to keep the rabbits. So if Mrs. Brown's students want their rabbits to have as much room as possible, how long would each of the sides of the pen be? First off, we should probably ask the question, does it matter what the dimensions of the pen are? Will that actually affect the area? So let's quickly take a look at that. And let me give you two examples here. So we've got 24 feet of fencing. Let's suppose we decide to make one side 2 feet, and that would make this side 2. That would leave us, well, 2 plus 2 is 4. That would leave us with 20 feet of fencing left over, so we'd have 10 and 10. Notice 2 plus 10 is 12, plus 2 is 14, plus 10 is 24. What's our area there? Well, our area is length times width, which is 20 feet squared. That's how much area you have if we made the dimensions 2 by 10. And so sometimes we want to think like it's always going to be that same amount in the middle, but it's not. Let's suppose we made just one side 1. That would make this side 1. That would leave us with 22 feet of fencing left. Put 11 on each side. Notice 1 plus 11 is 12, plus another one is 13, plus 11 is 24. So the perimeter is 24 still, 24 feet of fencing. But the area is going to be 1 times 11, and that gives us an area of 11 feet squared. To me, this was like one of the coolest things that I saw when I was first studying math, because, you go out with some money, you buy some fencing, and you think, how can I maximize my money here? Or how much I'm spending on material to give me the most space here for, in this case, pigs. And so obviously building your shape can affect how much room they have to run around in. So that's a 2 by 10. What if I made the sides 3 units long? So these aren't drawn to scale, obviously, but that leaves me with 18 left over, because 3 plus 3 is 6. Subtracted from 24 is 18. Divide that by 2, and we get 9 on each side, and that leaves me with 27 feet squared. So we're going to go through and look at all these possibilities and see what maximizes the area. Because at some point, this thing isn't going to keep going up and up and up. It's got to start going down. And so that's what's cool about this problem here that we get to solve. So if we go back and look at the questions, it says, that's one thing we want to know, is what will maximize that. And it says to begin by drawing 2 or 3 examples of what the pens would look like. Hey, we already did that. And then complete numbers 1 through 6 before we answer these questions A and B here, okay? So I should have this link somewhere in here, this sheet right here, so you can take a look at it. This is our first thing we want to do here. So it says number 1, make a table of the possible measurements for the rectangular pen. And so, and then record the length, the width, and the area of each pen. So fairly simple there. If the length of one side is 1, then the width must be what? Well, it must be 11. We just did that one, right? If the length is 2, then the width must be 10, right? If it helps you, you can look at length and width right here. Remember, if this is 2, and then the length must be 10, because these two sides must add up to be half of 24, or 12. So 1 plus 11 is 12, 2 plus 10 is 12. If we have a 3 here, this becomes 9. 4 becomes 8. We're basically taking a foot from the width and adding it to the length there. 5 and 7, 6 and 6. And then if we make it 7, we get 5, 8, 4, 9, 3, 10, 2, and 11, 1. All right. Now it wants us to find the area. Remember, area is length times width. 20, 27. Putting my multiplication skills on display, aren't I? All right. And notice as we get further and further down, at some point, our numbers start to go downhill as far as area goes, right? And so it looks like we max out right in there. So that's going to be probably our answer on one of them. But let's continue on, because it said to answer, questions 1 through 6 before we answered the front page. So this says to use the length and area to make a list of ordered pairs. And be careful with this one right here, because a lot of students want to make the length and width our x and y. This thing says to do length and area. So length is our x value, and area is going to be our y value. So that's all you're going to do is fill out this chart right here with what you had up here. So we've got the numbers 1 through 11 right here. And then make sure that you're putting the area, what's written in pink right here, for our y value. And I'm doing this in marker because marker tends to show up when I'm writing. It shows up better on our drawing or our camera here. But if you're doing this at home, it's probably better if you use pencil or pen, because it's easier to read. When you try to write small, it kind of jumbles together. Number 3 says to plot these ordered pairs on the graph paper provided. Now, I purposely gave you a graph paper that is numbered like this. So that way, and it's kind of like just quadrant 1 there, so things show up easier. So that's what I'm wanting to graph here, are these ordered pairs. So 1, 11, 1, 11. And I'm going to just plot the points real quick. I'm going to pause it so we can skip ahead. And boom, you should have something like that right there graphed, right? So there's your points. And if we connect these dots, let's go and connect them. Remember, we're getting a parabola here, which is a good thing because we're currently studying quadratics, right? There's our parabola. And so what this also kind of tells me is, we've been using just whole numbers here. It can kind of give me a good estimate of what the area will be if I make, the length like 1.5. I can go over to 1.5 and go up on the graph and get a good estimate of what the area of that rectangle is going to be. So that's what's nice about that. So that was number 3. Number 4. It says, what kind of equation is represented by the shape of the graph? Guess what? It's a parabola, right? Or a quadratic equation is what we're going to be looking at. And now it says to determine the equation that represents this graph. So that's what we need to do next. And then how does the graph you draw relate? And we'll worry about number 6 here in a second. So let's go back and look at this right here, these situations that we drew at the beginning, because we're wanting to come up with an equation that represents, like, you give me a side length right here, we'll call it x. So this is going to be our side length. And I'll tell you what the equation for the area is going to be. Well, if this is x, how do we come up with this side length? Well, we subtracted it from 12, right? So this would be 12 minus x right here. Notice, does that work over here? 12 minus x, 12 minus x. Does that all work? Well, x is 3, 12 minus 3 is 9. X is 1, 12 minus 1 is 11. X is 2, 12 minus 2 is 10. So yeah, that works. Let's now write it out a little more clearly just by going to a blank rectangle and saying if this side is x, this side is going to be 12 minus x. So those are the dimensions for this pig pen, okay? And now we can write out the area by saying length times width. So x times 12 minus x. That's the area that we're looking for. Well, let's distribute. And we end up with 12x minus x squared. And if we put this in standard form, we're going to get negative x squared plus 12x. And this should be our equation here. So that's the answer to the problem we just had. Where was it? So we say quadratic for that. Determine the equation. You can even write it out fancy and put f of x right there if you want to, and it is negative x squared plus 12x. A couple things to keep in mind here. That negative right there tells us that the graph got flipped, right? And that's what happened. With that negative there, look at the graph. Look at that. It got flipped, and that tells us we're going to have a maximum value. If it didn't get flipped, we're going to have a minimum value. And there is no bound on the maximum, right? Like the area could be whatever it wanted. But this works out for us because we know that there's got to be a maximum value in the area of this rectangle. And so because it's flipped, we know the max is going to be at its vertex, okay? So it says, how does the graph you draw relate to the size of the pins? That is, what is the graph showing us? Shows us there's a maximum and where the maximum is. Now, a couple of other cool things about this. Let's say I gave you that equation and told you, find the maximum. Notice where the maximum occurs. It occurs at the vertex. So I could have asked the question like this. I could have said, the equation for that pin is negative x squared plus 12x. Find the maximum. And you could do that. And we're going to get to that here in a moment. And I've seen these equations all the time when I was in high school. I would look at, say, the word problems there at the end of the problem set in each textbook. And it would say something like the arch in St. Louis follows the parabolic equation, blah, 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 blah. And I'm always wondering, like, yeah, that's real nice. Yeah, I can find the maximum value. How tall is that St. Louis arch? But where did you come up with that equation? You know, that's what I'm always wondering. When you talk about a ball being kicked in the air in physics and you're finding the maximum height of that ball, where does that equation come from? So they're different reasons. You know, this one is just the area of a rectangle. There are different ways that these quadratics naturally occur. With physics, it has to do with acceleration of gravity and things that we can dive into when we talk about it in physics. With the area of a rectangle, it's simply length times width, and we can come up with a quadratic equation. So these things, you know, I want to tell you that, you know, we don't always show you how we come up with the equations, but sometimes they're pretty simple to come up with, like we did with the rectangle here. And so let's say I gave you that. Let's say I said negative x squared plus 12x is the equation for the area of a pig pen, right? If it's shaped like a rectangle where you have a maximum of 24 for the perimeter. Find the maximum area. So same question. We know it's going to have the same answer. Maximum area is 36. But I want to know, how do we come up with it from the equation? And so that's when we're going to go back to that last video we did. We talked about using a quadratic formula to find the axis of symmetry and the vertex. Let's go ahead and do that. Let's use that negative b over 2a. That equals x. That is our axis of symmetry, right? So let's put it in. So remember, in this equation, my a is negative 1. That's your A. Your B is 12. And then your C is what? It's plus 0. That's my C. Well, I don't even need C because we're not dealing with quadratic formula right now. We're just talking about that first part of it, negative B over 2A. Well, negative B is going to give me negative 12. And then 2 times A is going to give me negative 2. And this equals 6. So x equals 6. That is my axis of symmetry. And if we look at the graph that we just made, notice the axis of symmetry, let's draw our nice straight line right here on it, is going to be at 6. Boom. There it is at 6. Now that doesn't tell me what the maximum area is. Remember, the x-axis is what? It was the length of the rectangle. The y-axis is the area. So I need to know what the y value is to figure out the area. I'm still pretending like I don't have this graph here. So I've got this right here. I know my axis of symmetry is at x equals 6. That tells me that the vertex is at 6 comma something. How do I figure out what that something is? Because that will be my answer for the maximum area. Well, I'm just going to simply say if the f of x equals negative x squared plus 12x, then the f of 6 will give me my y value. So I'm going to put 6 into the equation. Remember how we do that. We say to find the f of 6, I'm going to write out the f function, everywhere I see an x, I'm going to put a set of parentheses. And then I'm going to plug that value of 6 into the equation. 6 squared is 36, so I get negative 36. 6 times 12 is 72. And negative 36 plus 72 is 36. Remember, my y values are representing area. This is my max area. And because I also like to teach physics, always put your units in there so we get feet squared, 36 feet squared. All right, let's see if there's, what other questions do we have on this? So we did numbers 1 through 6 now. It says, how long would each of the sides pins be if they were only 16 feet, okay? How long would each of the sides of the pin be if they had only 16 feet of fencing? I think to clarify that question, we want to know for the maximum area, how long would the sides have to be? How would you go about determining the pin with the most room for any amount of fencing? What is the generalization that you could make? I'm going to leave these questions open because this is, I don't want to give you all the answers, but I'm going to leave these questions open for you to figure out on your own. We did answer this one though. And then we drew some examples. We did all that. So everything right here, I want you to finish this on your own. If I'm having you watch this on something like Edpuzzle, I'm probably going to leave that in the comments for you to answer. If you still have questions though, let me know. Hopefully this helped you start what we're going to call optimization problems. We're either trying to find the max value or a min value. And we'll see that in the next lesson where we're going to go over some more examples like this. But I think this is a great introduction. It's a practical problem. And honestly, I think it's pretty cool. So thanks for watching, and I'll see you next time.